the last lecture. If they should happen to find some, I don't know, vaccine that magically works like within the next month or two for coronavirus, then I'm happy to come back and show you some of the props I was going to bring today. I was telling Tom. I was telling Tom we were going to bring a steel bike, one of my racing steel bikes from the 80s, and then Steve was going to bring a carbon fiber bike that was relatively new to compare the two. So I'm welcome to bring those back sometime in the near future, and I'll hopefully, if everything goes right, I'll be here in the fall too. Anyway, so just to start our lecture here, last time we talked about topology optimization. We talked about the idea of a packaging volume. That's a place where you can put structure. All the places you can put structure. You can't put structure through somebody's head if it's an interior of a car. You have to leave that out. We talked about discretizing that volume into elements and then assigning a density to each of those elements. So if you have 1 million elements in your finite element model, that means your design space is 1 million, right? So there's a homogenization approach which allows you to take that density and translate it to a stiffness matrix for each element. And a mass for each element. And then you constrain the amount of mass that you're able to distribute through the volume. So the optimization becomes choosing densities for each of those elements, okay, and then taking all those elements, calculating out, using finite element analysis, calculating the strain energy for each of those elements, then adding up all those strain energies. And the place where the aggregate sum of all those strain energies equals to the minimum, that's where you get the lightest, stiffest structure. And this is an example that I've sort of just done by hand here because I already knew the solution. But as I had mentioned previously, we did this with car bodies at Chrysler. And this is a SUV body that you can see the packaging volume here. This had like 2.3 million elements. And we scaled this up. And the results, the topology optimization, the most efficient load passer, in that weird looking green structure there. This included certain boundary conditions, front impact, rear impact, bending, torsion, side impact, etc. And here's another view of the structure we got. One thing I found really useful was to go into the optimizer, and at least Genesis will show you where it's placed the density on these graphs here. So this is a cross-section through the packaging volume where red is the place where it's decided to put the most mass, the highest density elements. And this is actually really useful because it gives you a better idea of exactly where the load paths are, where they're really focused. You can see some lateral or some longitudinal sections as well that help you see that. When I left Chrysler, I was trying to figure out a way to use this information to estimate a weight savings. So the question I always got was, okay, Don, this is all great and stuff, but how much weight is this really going to take out? I don't know. We have to try to figure it out. No one liked that answer. My idea was to try to take this concept, or these plots, these density plots, and then use sort of like an image analysis software that material scientists use to try to calculate how much density is here, and then try to use that to compare it to a current body and then come up with some estimate for a weight savings. I didn't get that far. Maybe in the future. We also did this topology optimization on subcomponents. Here's a shock tower out of, this is actually out of the SUV, but what was interesting about this is that the topology optimization showed this space, this missing material here from the center of the shock tower, right here. And we carried that through to design, and then when we started looking online at competitive information, there's websites the car industry has where they tear down cars and take pictures. Here's a picture of a Mini Cooper chassis. And you can see right there that the material was taken out of the shock tower. So that's an example of where BMW had gotten to topology optimization probably well before Chrysler did. And there's much more examples of that. I'll show you in a little bit. There's some other tools I want you to know about that are similar to topology optimization. One of them is called topometry optimization. In topometry optimization, the design variable becomes the thickness of each of those metal panels that are welded together. Okay, so you can have 600 body panels or 700 body panels, and then you can assign a thickness to each of those, and then that becomes the design variable. Given certain boundary and loading conditions, the optimizer will then go through and choose the optimum thicknesses for every panel to give you the lightest structure. Another one is called topography optimization. As I'll show you in a little bit, a lot of car body panels have like ribs and things that are stamped into them. Those ribs can be enormously effective at stiffening, as you would imagine, and also perhaps likewise kind of same thing is they're also very effective at tuning the natural frequency of those parts or assemblies. So a big deal in cars is vibration, noise, vibration, harshness. I spoke about this before. And through using this topography tool, you can really go a long way towards tuning that natural frequency. So if you know you have some road input at some frequency that's exciting the structure, you can then tune that out by adjusting the bead structure. Another really useful tool is shape optimization. Shape optimization is a little bit more confusing. If you have a, suppose you had like one of the front rails on a car. I think I've showed you the structure in that picture there with the Mercedes structure. But suppose you've got a rail structure. So this would be the front of the car is this way. The front bumper would attach right here. You've got this section here. This goes back to the firewall. Okay, let's kind of see where this is. The shock absorber mount would be right up here. The shock tower. You can think of the cross section here. And if you look at that cross section, it's very often octagonal, for reasons I can explain if you're really interested. But what shape optimization does is you put so-called perturbation vectors at the surface of this cross section, at each, for example, node in the finite element mesh. And then you have some displacement that you put in as a starting displacement, a perturbation they call it. Okay, and then the optimizer can go through, and then the design variable is how big is that perturbation in each of those elements, each of those node elements. Okay, and then it'll displace things, and it'll work through different displacement degrees to create a shape that then gives you the optimized cross section for that part. And we at Chrysler we use this on the rocker panels. When I did some projects with U.S. Car, it's like a government-sponsored attempt to try to make lightweight cars, high-tech cars. We use this on front rails and rear rails to good effect. It's a very powerful tool. It not only tells you, so the first tool, topology optimization, will tell you where to put the structural member. Okay, this one will tell you what shape to make it, and then topometry optimization will tell you how thick to make it.
When you say the optimized cross-section, do you mean the cross-section that results in the minimum perturbation of each element?
No. What I mean is the optimum result is the lightest result.
Okay.
So the lightest, stiffest result, the one that would have the lowest the lowest aggregate strain energy. Okay. So the perturbation vectors move around the cross-section. So, one time it might draw it like this. And it'll go through and calculate how much strain energy there is in that section given the boundary conditions. Another time it might draw it like that. The perturbations change the dimensions of the part, the cross section. Different angles, different displacements in or out. Make sense?
Yeah.
So the perturbation vectors are changing this cross section and determining what's the most efficient cross section. But you can kind of see how this so nicely fits together. Like I said, topology optimization gives you the optimal load paths. Topometry optimization gives you the thickness of the panels, and then shape optimization gives you the right cross section. Probably I flipped the last two. Probably you want to do topology optimization first, shape optimization, then topometry optimization, and that gives you the most efficient structure.
Does shape optimization assume a constant cross section, or does it change it along the way?
You can put those constraints in. You can tell it a constant cross section. You can put in draft angles for a stamping, for example, to make sure you can get it out of the die. That's the neat thing about it. You can tune it to do whatever you want it to do. The last one I'll talk about is fiber ply orientation. So I'm sure you guys know about composite materials, and that composite materials, the best way to do them is to use unidirectional materials and then lay those unidirectional materials up at different directions to counter the loads that the part is encountering. Okay? So what the design variable becomes is the angle of the ply with respect to some global axis. So the optimizer will go through and calculate out the aggregate strain energy at different orientations of the plies, and then give you the lowest aggregate strain energy. So this one I know gets used in Formula One. There's a company, GRM, in England that I know a little bit, know the owner a little bit, and they've used this in Formula One. I'm certain this gets used in bicycles by a company like Trek or Giant or Specialized or Cannondale. It's a very powerful tool, actually. I'm not going to go too much into this stuff. These are some examples that we worked on that lightweight body project with that SUV about tuning the natural frequency of the rear wheelhouse. We use this tool very effectively on the lift gate opening to tune the natural frequency of the lift gate opening to get it so it was stiff enough. The hardest part of topology optimization for a car body is how do you translate those topology optimization results to sheet metal, right? Because you get this very blocky, almost organic looking thing from the topology optimization, but how do you actually make that into sheet metal? And that was a real difficult problem that we encountered, but fortunately we had very good design engineers, very good designing sheet metal components. And the final design is shown here. This was published in a paper I published with some other guys back in 2008, and it shows how the topology optimization results, what the sort of distinct features that you typically don't find in car bodies got translated into real sheet metal. And the first one up here is this strap that goes from the bottom of the front of the rocker panel to basically the side of the shock tower, how we translated that from the topology optimization result to the actual vehicle. The shock tower, we talked about that, about opening up a space in the middle because apparently the stresses aren't that high. Some of you guys who are car enthusiasts, you've probably seen these strut tower braces. Anyone into cars? Anyway, a lot of tuners, a lot of people who spend a lot of money making their street cars faster will put in these braces that might go from shock tower to shock tower, and we actually saw those type of load paths in the topology optimization result.
So how does it work? Because I can think that, of course, due to the complexity of the shape, you could 3D print the car, but it would be so expensive that
Right.
we will never do something like that, at least in the next 10, 20 years.
Yeah.
But on the other hand, making so many modifications to the sheet gives you so many problems with the edge retention, because I've been studying that people producing cars actually have this problem, that when they cut the sheet metal, actually form a lot of cracks during the crack. And so doesn't it affect the properties of the final, I mean, from a safety concern, isn't it better at the point to have an heavier car, but with fewer surfaces where cracks can nucleate, rather than having a lighter car that can go faster, but...
Right, that's more efficient. Gee, I don't know how to answer that. I know NHTSA has done a lot of studies about what real-world lightweight vehicles and how real data on how many people get injured or killed in lightweight vehicles versus heavy vehicles, and I think the results were kind of surprising that it wasn't as bad as you might think it would be. That the lighter weight vehicles didn't necessarily result in more injuries. They didn't necessarily, their drivers weren't necessarily that much more likely to get hurt in an accident. I make fun of the Mini Cooper there, but the fact is it's a really nicely done body white structure. And I've brought it up twice here, as in one example, what not to do. But it's actually a pretty good structure.
Same thing with I don't know if you know about the smart car.
Oh, I know a lot about the smart car, right?
But actually the structure of the smart car is great. I mean,
it has very high integrity, but the problem is there's not a lot of packaging volume for energy absorption, right? That's the problem with the car. Yeah, you won't get breached, right? You won't get the second car inside the passenger compartment with you. But the amount of energy you're going to absorb with your body going into the seatbelt because there wasn't a crush structure in the front, that's a different story. The Lotus Elise has a very interesting fiberglass front crush structure that's actually very effective at absorbing energy, the way a Formula One car does. And it's actually, in front impact, it's actually not that bad. In side impact, it's probably not that good because it's so low that if you got hit in the side by a big truck, you're probably in big trouble. But the front structure is actually very good on that car. But back to the cracks, though. I've seen this. They use these special inserts that they put in the die to trim the part when they cut it, right? And a lot of times they don't do a good job, and they're sort of dislocated a little bit. So like they're like these very hard inserts. Like they use a higher strength steel around the perimeter of the die, the stamping die or the trim die. And they're supposed to be parallel, but sometimes they don't do a very good job and they're a little bit dislocated. And that little edge produces a crack. So the trim, like I said, you've got some trim die that's trimming out some part. And they have these little inserts that they bolt on actually on the side. That this does the actual trimming. This is the actual cutting surface right here. And they make them removable so they can replace them when they wear out. But the problem is that sometimes they're not they're not exactly lined up very well. And so the steel gets trimmed like that. And of course, right here, you've got an invitation for a crack. And I've seen this happen, actually. So it's a question of how careful are the people doing this, right? At Mercedes, this was less of an issue. At Chrysler, it was a bigger issue. Anyway, good question, though. So the side of the tunnel, we saw these spider web structures. We tried to duplicate that with these ribs. This load path that goes from the rear shock tower to the C-pillar, something we added. In the roof structure, you end up seeing a lot of K's and X structures. Okay, so this is, for example, this K structure right here. Here's an example of a K structure. We added that, and it's enormously effective at increasing the torsional stiffness of the body structure when you can put something like that in there. And to this day, I've only seen one car that has that. There's a Volvo that's got a structure like that, but no other car, not even like a Porsche, Macan or a Cayenne, has anything like that. So there's a lot of opportunity there for increasing stiffness. I think the issue is it's expensive to make something like that because there's a lot of wasted material, right? If you stamp that out of a big rectangle, you're going to lose a lot of triangles and you're going to throw it away, scrap. So I think that's why this doesn't really become very feasible. And there's some structures on the bottom that we were able to duplicate with sheet metal. But once we had started seeing these results.
Is the conversion from the topology to sheet metal mainly done manually, or is it
yes.
generative?
Now, I don't know. I don't know how you could do it generative. I think you just need a really good CAD guy, a really good design engineer to do that. It's difficult to do. The term I used to throw around was steel origami. How do we fold pieces of steel in order to match the topology optimization results or efficient joints? I'll talk about that in a minute. Once we had the results, though, we started looking at a lot of the competitor vehicles. We had a huge teardown lab at Chrysler where all we did was tear down other people's cars. And we started looking at various cars and how they were similar. This is the bottom of a 2006 Toyota RAV4. And there's the topology optimization result that we got from actually a small Jeep SUV. And you can start to see the similarities. You can see these diagonal members that go into the inner rails here and here. You can see these diagonal structures that go from the front rail to the rocker panels. I should probably explain this. This is the front of the car. This is one rail. This is another front rail, and then this is a rocker panel. This is a rocker panel. The gas tank would normally sit right about here, okay, and then the spare tire is usually right about here. So this is the back of the car. You guys see where this is? Okay. So if you see where this is, you can start to see how these structures actually line up very nicely, that you begin to see a lot of the structure being translated from a topology optimization result to a real car. Again, this was proof that Toyota had been at this long before Chrysler had. Here's a Honda Accord. And when we were at conferences, we started talking to a lot of the Honda guys, and it turned out they had been using topology optimization for a long time to design their body structures. And actually, I think Honda's been one of the best at actually doing translating these topology optimization results to real structures. And in this Accord here, you can begin to see a lot of the same structures, like this diagonal member. This is the trunk opening. So if you're behind the car, you open the trunk lid. This would be like right there. You can see this diagonal structure they put in. The rear wall. So this is behind the rear seat, where your kids might sit. You can begin to see these structures that also look very similar to topology optimization results. And the colored material, the red and the blue, these are places where Honda's used high-strength steel. And the white is a low-strength steel. So you can really see where they use the high-strength steel in the primary load paths. And then for the closeout panels, the things that just are keeping water and wind and gravel out of the inside of the car, there they will use a less high-strength material. So they'll save money on using these, making these parts. These parts are just keeping wind and water out by using steel like a really easy, deep drawing quality steel. Then in the load paths, they'll use the more expensive structural steels, the high-strength steels. Here's an Audi A8. This is the aluminum Audi, big Audi, the S-Class competitor. And this is made out of a lot of very interesting extrusions, aluminum extrusions and aluminum castings. And you can very clearly see here some of the topology optimization results. You can see with the shock tower, the V structure that turns into the shock tower. This is where the shock would mount on the right side of the car. This is where the shock would mount on the left side of the car. You can see the rail structure. This is actually a casting here. These are extrusions. This shock tower structure is definitely a topology optimization result. And then there's this strap right here. Kind of see that right there that goes from the rocker panel basically up to the shock tower. A lot of similarities here. You look at the Audi A8, and we had one of these taken apart at Mercedes. You can very quickly see the topology optimization results and how they've optimized the load paths using topology optimization. Okay, so that's all I had for topology optimization today. Any questions on this one? Very, very powerful tool. Have you guys seen that at all here? Do they have that as part of the curriculum or anything? Or okay, well, that's good to know.
It depends on which course you are.
Yeah, but do a lot of the MEs get this kind of thing or not? Yeah. Okay, that's good. Okay. Okay. So the next lecture this is what's supposed to start today, and this is kind of a fun lecture. I was going to talk about a couple other bespoke items having to do with structural optimization, and then show some examples of bicycle frames, and show some examples of how body structures on vehicles, on cars have developed over the past, 60 years. One thing I want to talk about first here is joint efficiency. So we talked about this a little bit with the lugs on the bicycles. If you have one tube, if you have one load path this way, you have another load path this way, and you're pushing on this tube, okay, or pulling on this tube, but this is a very thin wall, you're not going to transfer that load very efficiently. Very important point. You can have the best load paths in the world, you can have the best thicknesses chosen for every panel, but if you don't have efficient lugs, efficient joints, then you're in trouble because you'll just lose a lot of that stiffness in the joint. I've read some papers on this. The most efficient joints are the ones that have shear panels, they call them, at all 6 locations where those panels join. So might be hard to imagine this, but you can kind of think of, like I said, these 6 different shear panels. You've got this tube going into this tube, and then you create a shear panel at 3, 4, 6, and 5. I think 2 and 1 automatically kind of exist, but trying to get those other panels in there. So by doing this, if there's any axial load on this tube, you can see how it would very efficiently transfer into the other tube. Okay, so this is just like the bicycle lugs we were talking about. The bicycle lugs really provide a very similar effect to this. They provide that joint stiffness that you really need in order to have an efficient structure. I tried one, I don't know, for about a month or so, tried to figure out how you could fold up steel to make a structure like this. I never really succeeded. If you come up with one, let me know. But this is really where it's at. This is a really critical part to structural optimization, is to make sure you have efficient joints. Another factor I don't want you to forget about is fatigue. So very important. The first aluminum knuckles that we built for the early Jeep Grand Cherokee it was the first time Chrysler ever made an aluminum front knuckle. And by the time that we put enough material back into that part so that it would meet fatigue requirements, durability requirements, it was actually the same weight as the cast iron part. We weren't using very high quality castings. They were just like, gravity castings or high pressure die castings. But something to think about. So certain materials have what's called a fatigue limit. You guys probably know this already. Certain materials don't have a fatigue limit. A fatigue limit means that particular component made of that material can go infinite number of cycles at a given stress level and never have to think about failing. Something to keep in mind when you're designing these parts is, is this thing going to fatigue or not? The beautiful thing about steel is it does have a fatigue limit. Bad thing about aluminum is it doesn't have a fatigue limit. So with aluminum, there's always some combination of stress and cycles where the part's going to fail. Always keep that in mind. Titanium has a fatigue limit. I think, if I remember correctly, I think nickel might have a fatigue limit as well. And to the materials design perspective, this has to do with the stacking fault energy of the grain boundaries and how easy it is for dislocations to traverse over a grain boundary. That's what provides the difference between a material that has a fatigue limit and a material that doesn't. Remember this one, okay? Okay, bicycles. So here are a bunch of bicycle frames going back to 1970, okay, and up till today. This, starting here with this Colnago, this was sort of the state of the art for decades, where you use a chromoly tube or manganese moly tube, okay, depending if it was Reynolds or or Columbus. These are two manufacturers of bicycle tubes. And then you would braze them together with a lug in between. Okay, the lug is, show you the next, oops, here we go. Here's a lug. So the lug is a sort of like a fitting, a glove that fits over the two tubes and joins them together. Okay, that was the state of the art for decades and decades. Many, many Tour de France's were won on that design. The issue is that when you braze these things, you got to make sure the steel doesn't get too hot, or else you could change the microstructure substantially enough that it wouldn't be as strong anymore. This is why they went to things like tubes that had thicker cross sections just right where they're getting welded, and then they were thin in the middle. The really good manufacturers, some of them use silver solder because the melting temperature is much lower for silver than brass, so you could heat the joint up less and retain more of the strength of the joint. Back in the 70s, the lugs were made by artisans who would take tubes and maybe weld them together, then file away and create these things. It was very expensive. It wasn't really till the mid-70s that they started using investment cast lugs. I think Mazzi claims they were the first. Mazzi is a Italian bicycle manufacturer that eventually moved to California, but they claim they were the first people to use an investment cast lug, and that technology was prevalent up through the mid-90s, I guess. In 1973, somebody made the first, Teledyne made the first titanium frame. You can see the tubes aren't very big in diameter, and the problem with this frame was that it was very flexible. Titanium has about 2/3 the Young's modulus of steel, so it never really worked very well, and that's why it didn't really sort of catch on in popularity. Carbon fiber actually came in the late 70s, believe it or not. They used a cast aluminum lug, and then they used structural adhesive to bond on sort of a pre-made tube. That tube might have been made through braiding, for example, or another process. Vitus made this technology popular in the mid-'80s, okay? And the problem is they didn't quite have the structural adhesive fixed. They didn't quite know how to do structural adhesive properly. And these frames inevitably failed by the joints ungluing or debonding. So I actually had a friend who used to race on this frame, and he actually went out for a sprint one day at the end of a race and pulled the bottom bracket out of the C-tube. So he pulled, this is the bottom bracket, this is where the cranks go in, this is where the bearings go, where they spin, right? He actually went out for a sprint and he pulled this out of this tube. It actually debonded and came down. So he went to pedal, all of a sudden the pedal went down as this whole structure flexed downwards because there was no bond there. I don't know that any of these frames, you can't even find these things on eBay. I think they all failed eventually. In the late 70s, Reynolds, which is a British company, started making a heat-treated steel material. So it was a chromoly or moly-manganese steel that was heat-treated. Okay, and this frame had to be silver brazed. Could not be brass brazed. It had to be silver brazed because the brass was such a high temperature that you would lose the heat treatment on the steel. They had some special test. If you were a frame maker, you had to take some special test to prove that you could weld these tubes together or braze these tubes together without losing the heat treatment. And there's actually some famous frame makers who weren't able to pass the test. So you don't see a lot of these Reynolds 753 bike frames because not many people could actually weld them. I think the steel was actually developed initially for making oxygen bottles for people climbing Mount Everest. Chris Klein. Chris Klein was an MIT graduate. He was here, I think, in the early 80s or late 70s. And he was a bicycle rider, and he came up with this idea of using these large diameter aluminum tubes that were TIG welded together. And I think Cannondale later sort of stole that idea, or I'm not sure, I don't know. I'm pretty sure Chris Klein was first, but some people say Cannondale was. I don't think that's true. And this company, Klein, they were successful for many years, and then they got bought by Trek. And then Cannondale was left being the person making big tube aluminum frames, which they still do. The first monocoque carbon fiber frame, so monocoque meaning that the tubes are not discrete. They're not like this frame here where they're bonded into joints. In this frame, the fiber is laid up in plies, and it goes over and around the joints between the lugs. So you have continuous fiber around those lugs. That gives you continuous load transfer around those lugs, which is a much stiffer, stronger, more reliable structure. This thing, as you can see, is pretty robust, and it probably wasn't that much lighter than a steel frame at the time. It was darn expensive, I remember. But you can see that it's, there's probably some overkill in material here because I don't think they necessarily had the technology at that point to compact the carbon fiber to make sure there was no voids in the polymer matrix, that it was all, the resin was all squeezed out as they laminated this carbon fiber. In the late 80s, early 90s, Merlin was a very, very popular titanium frame. What's his name? Rob Vandermark is from Somerville. And these frames were all, I think Merlin was actually in Somerville or Cambridge or Watertown. This name eventually got bought by somebody else and they refound the company as Seven Cycles. So Seven Cycles is still in business. They're still making titanium frames that are very much like this. They use a bigger diameter than these guys did. And they're in Watertown. I've actually driven by their plant. But these guys are still making frames. And they're big diameter titanium. A lot of people swear by these things. A lot of people say they're not stiff enough. I've never ridden one. I don't actually know. But they're works of art. If you ever get a chance to go in a bicycle store and look at these things, the quality of the welds is just amazing. Just beautifully clean and uniform. Yeah, they're pretty neat. They're pretty neat bikes. They apparently last forever because of the fatigue resistance of titanium, right? It's better than aluminum. That's sort of the idea of this idea. It's for stiffness, and the idea is that you want to lower the stress low enough so that there's enough cycles left in the frame that'll last at least your lifetime. I think it usually works too. Giant of Taiwan, they've become the 800-pound gorilla in the carbon fiber frame business. They took this monocoque concept that Kestrel developed and they perfected it with very disciplined, repetitive labor. Okay, that could make these plies exactly the same way every time in all these different frames, and they had enough capital to buy expensive steel tools to make these things, which allowed them to compact the carbon fiber more efficiently, to get a higher volume fraction of fibers. It's amazing. It's amazing what they've done. I mean, these guys stamp out. Giant makes frames for all the big manufacturers. They make frames for Specialized. They make frames for Trek. They make frames for Cannondale. They make for Cervelo. They make all those guys' frames. So anyway, the way they've set up the factory, the way they've perfected the process, I think that's what's really amazing. These guys even make their own prepreg where they combine carbon fiber together with epoxy into its sheets. Amazing what these guys have done. And I don't know. These new carbon fiber frames just ride amazingly. So if you get a chance, try it out. I was going to bring one today, but anyway. So Reynolds 953. This is a steel developed by Reynolds in England. This is a marging stainless steel, and it has like a 2 gigapascal yield strength. It's incredibly strong, and fatigue resistant. The fatigue limit scales with tensile strength. So these frames from Genesis, and there's a couple of people who've made these things out of this Reynolds 953, are incredibly strong. Okay, the problem as I see it is that they're not necessarily that stiff. They don't have that stiffness efficiency because the tubes are very close to just being round. There's some degree of sort of flaring the tubes. You make them a little bit bigger around the joints and so forth. They've done a great job. I'm not trying to criticize it, but the issue is that Reynolds, I think, as a steel company, has very much ignored the geometry side of this and really only focused on the material side. But anyway, a lot of people say these are great frames, strong, fatigue resistant, energy absorption, some people claim. I don't know if that's true or not. This bike here is interesting. This is a frame sponsored by ThyssenKrupp. ThyssenKrupp is a huge German steel concern. They're German. And interestingly, in about 2016 or 2017, I actually pitched the World Steel Organization on making a steel bicycle frame. So I can show you the presentation. I put a presentation together for World Steel that said, the Tour de France used to be ridden by steel bikes. Now it's ridden by carbon fiber bikes. You guys lost that market. How would you like to gain it back? And my point was exactly this, is that the geometry that's been developed isn't enough, that the stiffness of steel and the strength is being wasted because the geometry is insufficient. And could there be a way we could maybe make tubes through hydroforming? I also put together in this program, part of the proposal was to work with the Max Planck Institute outside of Dusseldorf, Germany, where they have a big steel research center. and we were going to develop a marging stainless trip steel so that we could have higher deformation. So trip steels are steels that go through a martensitic phase transformation, which gives them better strain to failure. You guys familiar with that at all, trip steels? So transformation-induced plasticity. It's a way that you can increase the strength, or you can increase the elongation of a steel without increasing the work hardening rate. Actually, you can have a much lower work hardening rate. So you can deform much further before the part breaks. So what I was trying to get them to do was to do a hydroformed part. So this frame came out like a year and a half or 2 years after I made that pitch. The pitch that I couldn't get any money for it, so it never flew. But it was interesting to me that this frame came out about a year and a half later out of this huge German steel company, which had no business making bicycles. This frame is a dual phase steel, and it has what they do with this is they stamp the two halves of this together, and then they laser weld it in the center. Tom, have you seen this bike?
I haven't seen this bike specifically, but I've seen the hydroform technique where they do two halves of the frame and just weld it on the sleeve.
Yeah, they do that actually Cannondale does that a lot on the aluminum bikes. But anyway, I find it very curious that this bike came out after I made that pitch. I didn't want to make it, I wasn't trying to get any money out of it. I just wanted to see steel frames get better, because carbon fiber frames scare me because they could delaminate, like I just showed you in that picture with that little piece of paint missing. The frame, it's not that light, unfortunately. They didn't really get really far down in weight. This is about an 18-pound bike at the end of the day, whereas the carbon fiber bikes can be well below the UCI limit of 16 pounds. But anyway, it's interesting they did this. I have the email of some of the guys who work there, and I keep meaning to email and say, hey, did I have anything to do with this? Okay, we talked a little bit about joining methods. Let's move to cars. Okay, so this is a Lotus Elite. This is the closest I think the car industry has ever come to making a true monocoque body structure. So a monocoque structure means that the outer skins of the structure become the stressed panels. So this is very different than what you'd call like a space frame. So like a steel bicycle frame is a space frame. You have discrete tubes that are loaded either tensile compression or torsion. Well, no, I guess a true space frame is only tensile or compression. But the point is that if you have like a race car that's made out of a tube structure, the body panel, the outer surface, is just really it's just cosmetic. It keeps the wind and the water out. That is the opposite of a monocoque structure. A monocoque structure is more like an egg, like a chicken egg, where the outer structure, everything is fully stressed. That's an egg structure. That's a full monocoque structure. This structure here, made by Lotus in 1957, the late 50s, is made of about 3 big fiberglass pieces that are laminated and then bonded together. And this vehicle was very light. This vehicle was around 1,200 pounds. It wasn't safe, but it was around 1,200 pounds. You can, every now and then you see these things coming for sale. They go for crazy money. But this is the closest I think anyone's ever come to a full monocoque structure for a car body. This is an interesting frame. This is called a Maserati birdcage. This is one of the few true space frame body structures that have ever been made. And you can see it's got this really tight lattice work of little tiny tubes that have been welded together. They called it a birdcage because the idea was that if you put a bird in there, it couldn't get out. It would form a cage. Lotus was the first company to move this monocoque structure to Formula One. Prior to that, Lotus 25 in the early 60s, all the Formula One cars were made from space frame structures that were little tubes that were welded together. Lotus took aluminum panels and bent them in various shapes and then welded them together, and they made a true monocoque structure where the outer structure, the outer skin of the body structure was the primary structure. It was the Lotus 25. And then in the late 60s, in 1967, they came out with the Lotus 49. This was also a monocoque, okay? But what was interesting about this vehicle is that this is the first time they used the engine as a structural member. That was really cool at the time. So Colin Chapman, the founder of Lotus, his philosophy was that any given part on a car should serve more than one function, okay? It can't just be keeping wind and water out. It can't just be to make the gear shift lever work. It also has to support some other function of the vehicle. So he looked at the engine and said, well, the engine shouldn't just be making power. It should also be holding up the back end of the car. And this is Lotus 49 was the first time that they created a monocoque for the front of the vehicle, and then the engine was placed between the rear suspension mounts, which were on the transmission housing, and the front monocoque structure. So the engine here is a structural member. Pretty cool. This is like state of the art for Formula One for decades now. Every Formula One, pretty much since the Lotus 49, has used a similar arrangement where the engine is the structural member. Ducati motorcycles, BMWs too. They use the engine. I think most motorcycles actually use the engine as a structural member now. Same idea. There's been a couple cars out there, passenger cars, that have a similar strategy. The Pantera of the 70s. You guys know what that is? Use the engine as a structural member. The Ferrari F50 was another car that used the engine as a structural member. I should probably put pictures of those in this presentation. The problem is that there's a lot of vibration involved. When you've got the engine bolted directly to basically the backside of the seat, that vibration is going to come up and drive the passengers nutso. So this is why car companies don't do that, because it's a comfort issue. But it's important to note here that this is like a fundamental difference between racing cars and passenger cars. In a racing car, you tell the driver, I don't care if your fillings, your teeth are going to fall out, deal with it. The car is going to be faster and lighter if it has this monocoque and structural member, engine is a structural member, okay? Passenger cars, you can't really do that. But do you guys see a really neat opportunity with something Elon Musk has done recently? When you've got an electric motor, the vibrations are much lower, right? So all of a sudden, the possibility of using the housing on the motor becomes possible, right? You might be able to use that structure on the electric motor because it's not vibrating as a structural member. And I guess that the concern there is, okay, if it's a structural member and it strains, what's the gap between the rotor and the stator, and might they hit if it strains too much? So I don't know where that's. I don't think anyone's tried it yet, but it's a thought. What the electric car companies have done is they have used the battery housing as a structural member. BMW has a scooter that they sell in Europe where the battery housing, there's like the front of the battery housing has some mounting points, and the back has some mounting points. The steering system, actually, like the forks and everything, they mount directly to the battery box, and the rear suspension mounts directly to the battery box on the backside. So the whole bending load taken up by the scooter is taken up by this battery box. Anyway, keep that in mind. Always keep that in mind. Can you use your structure to do multiple things? Some of the Lotus Formula One cars, back when they were space frames, they actually used the tubing as waterways for the radiator. So the radiator was in the front of the car, the engine was in the back of the car, and then there was structural tubes that made up the primary structure of the vehicle. They had water running through those tubes. Okay, so they would use those tubes not only for structure for the vehicle, but also in place of radiator hoses. The only problem with it is it might rust after a while, but they're racing cars, they don't have to last more than one race. I love this picture. This is a Porsche 917. If this picture doesn't make you get out of bed in the morning to become a material scientist or a structural engineer, nothing will. I look at that and I go crazy. Like you look at the seat and you look at the size of the car and the size of the tires and this enormous engine in the middle. Crazy unsafe, but perfect for a racing car. This actually it's a true space frame design, and these were aluminum tubes on the original Porsche 917s. Your feet actually were in front of the center line of the front wheels. So if you got in a front impact, you lose your ankles basically. Completely unsafe, totally unsafe, horrible car if you got in an accident. But if you're not planning on hitting anything, that's a big if. It's just an amazingly structural efficient design. And these cars were incredibly light. The engines were made out of magnesium. They went through all kinds of crazy stuff. They talk about the balsa wood gear shift handle. It's a fiberglass seat. Very, very, very interesting structure. The Porsche, here we go, the McLaren, the 1981 Formula One McLaren. This was the first semi-monocoque structure for a Formula One car to be made out of carbon fiber. The Porsche 962. This was a sort of a tub design. I don't know if I would call it a true monocoque. It's sort of a tub design. It's made from aluminum sheets that are riveted together and probably welded together with, I think, honeycomb inside. My favorite, Lotus Elise. They use, as I explained the first day, they use aluminum extrusions as the primary load path that are bonded together rather than welded together using epoxy structural adhesive. The BMW Z8, very much close to a tube frame structure. And this structure is made out of aluminum extrusions that are welded together. Not a real light vehicle, but I put that up as an example because the load paths were so clean and well defined on that structure. You can I don't know, I look at this, I can very clearly see the flow of stress going from the front bumper basically to the middle of the floor pan. Let's see here, the Porsche Carrera GT. This is a carbon fiber monocoque structure. And what I find really interesting about this is this rear structure here. This holds the engine and the rear suspension. It's not quite a space frame. It's not quite a monocoque. It's somewhere in between. So I call this the mid-spectrum concept, where you have something that's not a space frame, which would be on one end of the spectrum, and not a monocoque, which would be on the other side of the spectrum, but something in between. If you look at monocoque structures on Formula Ones, they're very much understressed, especially because Formula One has weight limits. But the torsional stiffness, I have a friend who used to work at McLaren, so I know this. The torsional stiffness of a McLaren carbon fiber tub, for example, is about 60,000 Newton meters per degree. Okay, the best cars on the road, like this Porsche Cayman, is about 40,000 Newton meters per degree. Your average Toyota, Camry, that kind of car, they're probably around 20,000 Newton meters per degree. So at 60,000 Newton meters per degree, you have to ask yourself, do you really need that level of stiffness? What's it really going to do for you? And having spoken to a friend of mine who was an engineer at McLaren, he said that there was no reason to have it from a safety or a performance standpoint. It was only because the drivers like the feel of the stiffer structure. It made them more confident behind the wheel, which is important. So they keep doing it. But it brings up a key point, and that key point is that if you could look at the stress at every X, Y, and Z in that Formula One monocoque, this structure here in the lower, my lower right. If you look at that structure, you have to ask yourself, at every X, Y, and Z, is the material really that highly stressed? Or is there a lot of material there that isn't that highly stressed? And if you think about how we did topology optimization, you can very quickly, I think, deduce in your head that no, it's probably not. So there's opportunity there for weight savings. And that's what Porsche did, I think, on this structure here. So I wonder why is it more people aren't using that? Okay, the Audi A8, the Porsche Cayman, I mentioned those before. The Audi TT, the current generation, or do they still make this car anymore, the Audi TT? They renewed it? The second generation was actually a really neat car. The first generation was basically a Golf that had some body structure, or some cosmetic changes, okay? But the second generation was actually a very interesting structure because they used a multi-material solution. This is one of the first cars, I think, to really do that en masse. That they have the primary structural paths are made with high-strength steel, and then the closeout panels are aluminum. Now, there's a galvanic corrosion problem there, which I assume they solved. But it's interesting. They were able to produce this lighter structure by using aluminum where you didn't need the really mechanical capability of a high-strength steel. The BMW i3, my favorite car right now, very vastly underrated. You could buy them all day used for $10,000. First carbon fiber mass volume car. To me, that's a real milestone. They not only did they develop the technical side, but they developed the commercial side, which probably is equally as big a challenge in order to find a way to get that carbon fiber cheap. And then there's the Baskin One concept. So thinking about the two ends of that spectrum, the space frame, the monocoque, understanding that the monocoque might be understressed, understanding that there's technology out there that's been developed for bicycles where you can maybe very is the wrong word. You can somewhat inexpensively make carbon fiber bicycle frames. Okay? How can you marry those three? How can you find that mid-spectrum structure that takes advantage of the carbon fiber, uses the most efficient load paths, doesn't include extra material? So my idea, I actually published this in this book right here, was to come up with this structure right here, where the load paths are much clearly defined. The tops of the shock towers become the cowl, or the area that's underneath the windshield, and then the rear shelf becomes the structure that supports the rear shock towers. All those get integrated rather than having these dislocated load paths. And the parts are sort of made in chunks that really aren't that much bigger than a bicycle frame. So I don't know, if anybody has access to a lot of money, interested in exploring this concept, it would be, I think there'd be a lot of advantages to it. You could use the volume production techniques that are used in Taiwan to make carbon fiber bikes, make manageable chunks that mimic the absolute most efficient load paths to make a body structure. Okay, it's 10 o'clock right now. I've got one more wrap-up slide. If you guys want to go now, I'll understand. If not, I'll keep going. We have extra enough memory on the chip there to, okay. Okay, this is where we started. Structural efficiency is a function of geometry and materials. We have the ability to design geometry, that's clear. But what isn't so clear is that we also have the ability to design materials that are more structurally efficient. Materials that have a high yield strength to density ratio, as or both, a high Young's modulus to stiffness to density ratio. So those are the things that we can really design. We can really design fatigue resistance. We can really design strength. We can really design energy absorption. These are real things and real materials that we can design. So first we talked about what I just said about materials, designing materials that have these high ratios. We talked about dislocation theory, that dislocations really are the tool manipulating the way dislocations move through a lattice. There's ways we manipulate that movement to increase strength. We design ways to manipulate how dislocations move or they tangle up on each other. We call those strengthening mechanisms. That will give you an increase in strength to density. For an increase in stiffness, you have to go to things like using a composite, where you use a stiffer phase with maybe a less stiff phase to increase the stiffness of the overall material. Then we went to the geometry side. We talked about there's only a couple really modes of loading. Right? There's bending, there's torsion, there's buckling, there's tensile, there's compression and shear. We talked about how stress is distributed under those different loading conditions and how we can take advantage in certain cases of load being non-uniform in a cross-section of a material to increase strength and decrease weight, assuming you've got packaging volume. And we talked about this idea of going from a tube that has a small diameter with a thicker wall to a tube that has a bigger diameter with a thinner wall, which in net can produce a tube that's stiffer in bending or torsion than we could if the material was smaller in diameter. We took a complicated structure, a car body in white, the primary structure of a car, which looks very complicated on the surface. We broke that down into various beam elements. These various beam elements can be simplified. You can determine what loading cases on those out of the bending, torsion, tensile, compression. And then through knowing that, you can design each of those parts to take those different loading modes or choose materials that make sense from a cost perspective. We talked a lot about numerical optimization. When you have a design space, a multi-dimensional design space, how do you find the point in that design space that has a minimum weight or maximum strength or maximum stiffness? And fortunately, for centuries before us, there was mathematicians who obsessed about this sort of thing, and they developed all kinds of interesting mathematics for designing or for searching a multi-dimensional hyperspace that as humans we can't even envision in our heads. We can't begin to fathom what they're like, right? And search those multi-dimensional hyperspaces or design spaces for optimum solutions. We talked about using that type of tool using that type of mathematics to solve topology optimization problems. So what is the most efficient load paths? We talked about using density of different elements within that structure. Density becomes your design variable. You can choose some density between 0 and 1 for all those different elements. Then using these numerical optimization methods to find the place where we can find the right density for every element in the mesh to give us the lightest, stiffest solution. And we talked about joints. And we talked about the history of different cars and bicycle frames and how they've gone to become lighter and stiffer with time and safer. And this is all through understanding structural optimization and getting people together who understand both the material side and the geometry side. So with that, I'll say thanks for listening. And if you, I don't know, if you guys want to see some bicycle frames, I can bring them back in a couple months or something when the coast is clear here. And I think Professor Eggers asked me to teach again in the fall, so if you want to talk some then too. And you guys have my, I think you have my email address here if you want to email me. always feel free to. Is it on here? It's not on here. It was on here. Anyway, I think it's on the course syllabus. It's D. Baskin. D. Baskin, so D-B-A-S-K-I-N at Spectrum Materials, E-N-G. Don't forget the S at the end of materials.com. Thanks, guys.